Swayam Prabha. Digital India. Educated India.
Hello everyone, in this week we are going to talk about reactor problems, particularly focusing on catalytic reactions, heterogeneous catalysis, packed bed reactor, enzymatic reaction systems. Okay. So, today the first lecture we are going to focus on general packed bed catalytic reactor. I mean how we can model them and what are the background of this process. So, essentially we will be talking about heterogeneous catalysis problem in this case, and how the mass transfer in a packed bed column is intricately coupled to this catalytic reactor process. So, let us consider a simple catalytic reactors, and these catalytic reactors are very common in chemical industries, whether you go for catalytic cracking or you go for fluidized bed reactors, right. So, these are very common. So, let us assume this is my a simple packed bed where I have the catalyst particle, the packings on which the reaction takes place. So, the concept is the configuration is very much similar to the packed bed adsorption, right, except that here we are having catalytic reactions instead of adsorptions, right. So, this is a packed bed catalytic reactor where you have inlet from this side and this is the outlet. Let us assume a small cross section of delta z, but before as we always say that before working or writing out the model equations, it is absolutely important to write down the assumptions. So, what are the assumptions that we are going to consider in this model first? Let us say steady state operation to simplify our lives, right. Another important assumption we can make is that the velocity in the packed bed is of plug type, right. Cylindrical or tubular reactor or tubular reactor geometry. Also, let us ignore any radial transport. This is not a practical assumption, but at least for this problem essentially we can get a very realistic idea of the dynamics of the process model even without this radial transport mechanism, but this is of course I must say that this is an assumption that you should relax to get a more practically relevant idea. Mass transfer by convection, I mean this is something which we are also going to look into the case that, but let me just spell it out now, that for the time being we can say that the mass transfer by diffusion, let us say, is not so significant over convection, but you already know that in case of gas phase systems diffusive effects are very important. For liquid phase systems we can safely ignore any diffusive or axial diffusion can be ignored with respect to axial convection, right. And the particles are considered to be of uniform shape and size. Particles, catalyst particles of course, are of uniform shape and size. Now, let us try to make a overall mass balance over this elemental section of delta Z, or the species balance, let us say species balance across delta Z. So, what we get, we are only considering axial fluxes. So, N A at Z minus N A at Z plus delta Z. So, this is the change in the axial flux can be equated to the this accumulation, which is the reaction in this case, or the consumption, R A A C A delta Z is equal to 0. So, here R A is the rate of chemical reaction or the rate of catalytic reaction. This is very important, per unit catalytic surface area, right. So, whatever rate you are considering, that should be divided by the unit catalytic surface area. So, moles per second per meter square, right. AC is the external surface area of the catalyst per unit bed volume, because we are multiplying this with the bed volume in that cross sectional in that elemental section of delta Z. Unit bed volume. So, this is meter square plus meter cube, and all of you know this. So, this value of this AC is turns out to be 6 1 minus phi is the bed porosity divided by the particle diameter, right. This is something which all of you can also work it out, and I leave it to you. So, of course, phi b is the bed porosity here, dP is the catalyst particle diameter, and A is the cross sectional area of the packed bed. Right. So, considering the and of course, I have to write the flux. So, this flux in A has two components, the diffusive flux and the convective flux. Right, I just multiply with the area here. So, u0 is the plug flow velocity, right. So, we do not I mean, the other option is to calculate this based on the pressure distribution, either following Argon equations or Darcy's law. That is something you can also work out, or you can also have the Darcy-Brinkmann equation to calculate to estimate precisely how the flow variation or the hydrodynamics inside the packed bed happens, right. So, Darcy-Brinkmann is a I would say a generalized version of the Darcy's equation, which takes into account of the boundary wall consideration. Since Darcy's equation is a is a first order model, so you cannot incorporate the boundary conditions effectively, and for that Brinkman equations came into existence, where the boundary effects are very important. Now, let us say if you consider, let me write this in red, that if you consider that the diffusion is insignificant or small comparing to convection, so that the overall mass transport is dominated by convection alone, and this is likely the case in liquid systems, because liquid diffusivity, the diffusivity of the species in liquid systems are very small, and as a result Peclet number is high. So, so mass transport is generally dominated by convection in packed beds. Okay. So, if the mass transfer is dominated by convection, so this N A is proportional to U0 C A, right. So, we can write the main equation, I mean taking the limits of delta z tending to 0 as minus U0 dCA dz plus R A AC is equal to 0, isn't it? It is a simple first order equation, first order linear equation. Now, let us try to understand how we can write down this reaction rate here. So, any reaction, so for reactions which is at steady state, right, reaction happening at steady state, the molar flux of A or the species A on the particle surface, right, please mark my words, on the particle surface is equal, has to be equal, right, for mass conservation, is equal to the rate of disappearance of course species A from the surface. Right. So, at steady state, the flux or the molar flux of species A on the surface has to be equal to the rate of its disappearance. There cannot be any accumulation, right, at steady state. So, if there is a there is a particle or a catalyst particle, right. So, we say that there is a certain boundary layer, let us say the boundary layer thickness is delta, etc. So, the particle surface concentration, let us say Cs, and the because of the formation of the boundary layer, and the far away boundary condition is Ca. So, in this scenario, the whatever this flux that is approaching or incident on the particle surface should be equal to the rate of its disappearance, and how it will disappear? By chemical reaction only, right. So, it should disappear from the particle surface, and this is essentially, this is very much equivalent to the linear driving force model which we have just seen in the previous lecture on adsorption, right, which tells you that the linear in the linear driving force model, for the mass transfer on the particle surface, or the interparticle mass transfer effects, we also say the same thing, that the molar flux of the species A is equal to the rate of disappearance, and there the disappearance was due to adsorption, and here the disappearance is due to chemical reaction, right. So, this disappearance is due to chemical reaction or catalytic reaction. right. So, this has to be true, right. So, I can write down the chemical reaction rate minus R A is proportional to the mass transfer coefficient into C A minus C A S, and of course, I will draw this picture once again here. This C A S is the the surface concentration, and C A is the bulk concentration away from the particle surface, which is the bulk concentration in this case in the packed bed, right, and the thickness is delta. So, you can write this mass transfer coefficient as d by delta, is not it, based on the thickness of the boundary layer. That is how the film theory approach actually works. So, in most this mass transfer limited reaction, this is another important point, in most mass transport limited reactions, right, which is the case here, because we study the this mass transfer in the packed bed, right. So, in most mass transfer limited reaction, the surface means the particle surface concentration is negligible compared to bulk. So, which means that CAS is much smaller than CA, right. So, you can argue that what happens when it is not a mass transfer limited reaction. So, if it is not a mass transfer limited reaction, if mass transfer is not the slowest step in the process, then the system is dominated by reaction. So, we can just work out the reaction kinetics, and that will tell us that how the things change with time, right. So, there is no point of working out the mass transfer or the mass transport effects, right. So, it is only when the the mass transfer effects are important in the packed bed reactor, then this question of diffusion, convection, all this comes into the picture. But if it is a reaction limited process, or the reaction is the slowest step, it does not matter what is the rate of mass transfer to the process, then you can just write down the reaction kinetics for the problem, right. It is just like a kinetics, and whatever reaction is happening in the the catalyst particles, that will govern the entire system dynamics, because that is the slowest step. But since the time scale of the mass transfer is much larger in this scenario, and that is what we consider it to be mass transport limited reactions, in this case the individual reactions happening is quite fast, and that is not so important, and that is the reason why the catalyst particle surface concentration is much lower than the bulk concentration, because whatever is coming to the particle surface is immediately consumed by the reaction, or the reaction rate is much faster compared to the mass transport rate, and that is the reason why this surface concentration is much smaller, right. So, this is a very practical consideration that we are making here. So, based on this idea, you can easily realize that this R A turns out to be just K C into C A. So, we can write down the final equation as minus U 0, it is U 0 d C A d Z is equal to minus K C A C C A, right. So, this is a simple first order linear ODE, first order linear ODE, right, and on integrating you can easily work out the so for the boundary condition that at Z is equal to 0 you have C A is equal to C A 0, which is the inlet concentration. You have the concentration profile, I mean the solution to this equation C A as a function of Z is equal to C A naught exponential right. So, even with this simple even with this assumptions, with so many assumptions and some very practical consideration, you can find out that how the reactant, how this reactant concentration decreases along the length of the packed bed reactor, and this is a very, even though it is very simple, it is a very powerful relation in the context that you can actually work out that how the reaction rate varies in the reactor. So, the minus R A can be written down as like this. Right, how the reaction rate actually varies along the length of the reactor, and this can also be quite useful for estimating the size of the reactor, like what should be the degree of conversion that you want to achieve. So, if I try to make a plot of C A versus C A naught, right, along with Z, so this will be something like this, isn't it? And for different mass transfer coefficients, I mean, as K C is increasing, these profiles will look something like this. So, with higher mass transfer rate, the effective to have a desired conversion, the length will be smaller, right. So, this relation provides very useful information in respect to the design of the packed bed reactor, of course making some assumptions that there is no intra particle effects, because we have not considered any intra particle effects here. We considered the problem to be in steady state, which is normally the case for industrial practice. We also said that diffusion is not important for this problem. So, this is the case for liquid phase reactors. And this K C, how do you estimate this mass transfer coefficient K C? So, this mass transfer coefficient K C can be estimated from standard Sherwood relations, right, from standard Sherwood relations, and you will find several such relation in textbooks, in handbooks, in research publications. I mean, and these are some of the popular ones. For low Reynolds number, typically less than 40, you have this relation of Sherwood number as 2 plus some factor which depends on the shape and size of the catalyst particles or the packed bed cap particles. So, this is known as the very popular Frostling relation for estimating mass transfer coefficients in packed bed. For moderate Reynolds number, generally you do not obtain a situation of very high Reynolds number in packed bed. Sherwood number is F2, Reynolds to the power half, Schmidt to the power half, 1/3, right. So, this is known as Thames and Kramer's relation. You can also use the Colburn's factor J. So, based on the Colburn factor J, so which is equal to Sherwood by Reynolds Schmidt. If I am not wrong, this is Reynolds Schmidt to the power 1/3 or maybe Reynolds 1/2. So, this factor you get phi j, of course phi means phi b, 0.765 divided by Reynolds to the power 0.8 plus 0.365. There are some Colburn charts also available and which you can also refer. So, this is for the case of Reynolds number greater than 10. For ultra low systems, right, for very low systems, well, Reynolds number is much less than 1. For Reynolds number much less than 1, it is very reasonable to approximate Sherwood number as 2, okay, because that is the lowest Sherwood number that is possible flow past a sphere. This is a very classical textbook problem in that you will find in any transport phenomena book. that for very, the minimum possible Sherwood number or Nusselt number is generally equal to 2, and based on the assumption that it's a flow past a sphere, right, which will give you the minimum Sherwood number. So, in case of very low flow rate, which may be possible for liquid flows in porous mediums, highly impermeable or low permeability porous mediums, the Sherwood number can be easily approximated as 2. Now, let us revisit the condition or relax the criteria, relaxing the criteria that criteria of diffusion to be negligible. So, this is something which you have already made before. So, we will get N A is equal to, we have to use this full the diffusive flux into consideration. We have to take the diffusive flux into consideration, right. So, from here we can get, considering that flux has the components of the diffusion along with convection, and as I have said, this is for the case of gas phase systems, this is very important. So, what we get is that we have an additional term in this problem. Of course, the reaction part, that same thing is done here. We consider that reaction surface concentration is much less than on the particle, far away from the particle. So, now this is an additional term, this double derivative term is an additional term in this case, which is due to the diffusion. Now, just also to give you a mathematical perspective, if you try to non-dimensionalize this equation, just bear with me. So, non-dimensionalizing this equation based on the scalings that, let us say, Z star is equal to Z by L. We define the Damkohler number as, sorry. So, I hope all of you are aware of what do you mean by Damkohler number. The mass transfer rate by the reaction rate, and then you have the Peclet number, which is the convection rate by diffusion rate, dA. So, the same equation can be modified as 1 by Peclet number, right. Of course, C A star is C A by C naught. Right. So, this is the modified equation we get, and here clearly from the criteria of the Peclet number we can clearly see that if Peclet number is large, we can say that convection is important for the problem, right, which is true for liquid systems. So, diffusive term is not important, right, because 1 by Peclet number tends to 0, right. So, diffusive term is not important, and this equation reverts back to the previous case where we originally made the assumption that to ignore the diffusive term. That is something which I also say here based on the criteria of the Peclet number. So, instead of grossly making an assumption that diffusion is unimportant in the problem, you can actually frame the complete equation, evaluate the Peclet number and see that how much of the contribution this diffusive term is making in this problem, and based on that you decide, after non-dimensionalizing you decide whether to retain that term or to ignore that term. So, if you talk in terms of the perturbation methods, this 1 by Peclet number or essentially the Peclet number can be that epsilon parameter based on which you can also do approximate solution to this ODE or to this problem. But of course, there is a direct solution possible, but if you want, if the problem is slightly complex, let us say with the help of, if the reaction is second order or something, it's slightly complicated to solve out, right. So, in that case you can use this perturbation methods to get approximate analytical solutions over the expansion of 1 by Peclet number, isn't it? So, that is something that you can of course try out and look into the situations when you have diffusion important in the problem. So, when diffusion is important, of course 1 by Peclet number is not a small quantity, and that is likely the case for gaseous systems. Okay. So, with this I think we can close this lecture today. I think all of you found this theory of the packed bed reactor to be quite interesting and exciting. In the next lecture, we are going to talk about more on how the mass transport and the reaction effects takes place inside the particles or inside the particle pores. Thank you.